Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. So, this particular lecture we are going to see the extension of the dynamic control. So, in fact, it is actually like integration of kinematic and dynamic control. So, that is why people call it a dual loop. So, we will see like how the dual loop can be incorporated. In that dual loop, what we can have an advantage. So, we can control the kinematic level control on the task space, or you can say the task space position can be controlled directly. Then we will go to the dynamics in the joint space. So, what we get advantage, the tau we can directly get with the combination of mu and q. So, that is what we are trying to see. So, this some people call cascaded because it is a dual loop, or why we call cascaded, because the velocity we are actually like controlling based on the position control output. Okay. So, that is why it is called cascaded. So, now it is actually like two combined thing. So, the inner and the outer so would be controlling, that is why it is called cascaded. So, we will see even little more detail. So, for that one important condition, that the system what we call nonlinear system should be having in the form of input affine. So, what that mean? So, it should be any subsystem you take. So, that should be assigned with one, you can say, output or input in the other way around. So, this output is actually like affine with some input. So, for example, x2 dot is having a x3 as the, you can say, independent input. So, when you call x dot n, so that is actually like having an independent variable called u. So, if this is the form we call input affine system. Fortunately, our mobile robot or even our manipulator has this kind of advantage. So, what that mean? So, our robotic manipulator dynamic model and kinematic model can be written in this form. Okay. So, that is what we are actually like trying to write. So, since a robotic system is a second order system, so we should have a two, you can say, subsystem. One is x1 dot, the other one is x2 dot. So, the x1 dot can be written as q dot and x2 dot can be written as q double dot, or we can take mu dot and q double dot. So, like that we can take. So, we are going to take this mu dot and q double dot in the sense. So, x1 is actually like mu is x1 and x2 is actually like q dot. So, this is what we are going to take. So, for that we use robot kinematic model in the sense differential kinematic model as first subsystem, and the dynamic model in joint space is the second subsystem. So, now you can actually like see it so this way. So, here actually like we can actually like rewrite this eta double dot as so q double dot. So, in order to give consistency for us. Okay. So, because this is the most of the robotic community people call eta double dot. So, but we have used from conventionally q double dot. So, we can use it that. So, in that case what we can see, so we can actually like get it x1 dot and x2 dot in this form. So, now we can see like f1 of x1. So, in this case there is nothing because this is related to x2. So, in the sense, so your f of x1 is not having any value. So, I assume that x1 is mu and x2 is actually like q dot. So, then I can actually like find the other variables like this, right. So, now based on this what I can do, I can go to the what you call this cascaded control design, then I can actually like bring back what supposed to be tau. Okay. So, in that sense I am actually like taking only these two are the equation, based on this I am trying to derive the control design. So, in that sense what we are trying to do it, so we are actually like trying to take the motion control. So, what we assume that the mu decide dot mu double dot decide all obtainable, which is actually like from the trajectory planner. So, then we are actually like assuming that the actual position and you can say both task space and joint space are available, both task space velocity and joint space velocities are available. Okay. So, the forward and inverse dynamic model and you can say kinematic model are available, in the sense J of q and mu and q function inverse of mu and J inverse are available. Further, if you want to do it in model based control, then the inertia matrix and other effects are available. Since we are talking about cascade control design, that is modified version of computer torque control, you can take it. So, in that way, in that meaning, so the m of q and n of q comma q dot, we are going to use it. Okay. So, now we are trying to find out the control input. So, for that first we are taking two subsystems are independent. So, what subsystem we have taken, x1 dot and x2 dot we have taken, these two subsystems are independent. Then what we can say, so E1 is actually like x1 decide minus x1 and E2 is actually like x2 decide minus x2. So, these two error dynamics are actually like supposed to be stable. So, in that sense what I can say, so E1 dot plus K1 E1 equal to 0 and E2 dot plus K2 E2 equal to 0, which we have done in the kinematic control, the same thing. So, if it is a two independent system, this is possible, right. But what happened, the E2, which is actually like you are writing x2 decide minus x2, which is actually like you can see this is, so q dot decide minus q dot, whereas so you can see like the E1 dot, we are actually like getting the input which is actually like x2, right. So, in that case, so x2 decide I cannot give if I assume that these two systems are combined. Okay. So, then what I can do it, so if these two are not independent subsystem, then I have to bring that error also into case. So, that is what we are trying to do it here. So, the E1 is actually like this. So, E1 dot I am taking it here. So, now this x1 dot decide is actually like what I have it from the trajectory planner, but this x1 dot, so the x1 dot I can write it as, so function of x1 plus g1, so x1 into x2, right. So, that way if I relate, so what I will get, so this, right. So, this I can actually like substitute it here. So, what I will get, so the x2 I will get as a input, but you know like this is actually like obtainable where the E1 tends to 0 when t tends to infinity only if, so x2 equal to x2 decide what you are planning, or you can say x2 is actually like independent state, right. But you know like this is actually like coupled system, because the system is not having two subsystems, right, it is a single system. So, then we have to actually like bring that error. Okay. So, this is what the x2 decide supposed to be. So, but we are assuming this is the x2, but if this is not controllable, that is what I have written it here. If the x2 is a state vector of a second subsystem, it is one of the system feedback, not a control input, then what we can do, so we can consider instead of what we have derived here, so this x2 I can consider as x2 decide. So, then there would be error will come. So, this error if I converge in the second subsystem where tau is the input, if I choose a proper tau in such a way that this E2 tends to 0, then what happened? So, x2 tends to x2 decide. So, then what happened? E1 tends to 0. So, like that it is coupled, and it is actually like you can see like it is coming backward, right. So, that is why it is called backstepping. So, that is what we are actually like trying to see. So, now based on this what we can see, the x2 we can give this form. So, now if I substitute this into the you can say the first equation, the equation would be slightly different. So, now I am taking the derivative of this time derivative. So, E1 we know already. So, the E2 dot is x2 dot decide minus x2 dot, but what is x2 dot? So, x2 dot is nothing but, so q double dot. So, if it is q double dot, this we can write as, so m of q inverse into tau minus, so n of q comma q dot, right. So, that I can use, then I can actually like make it. So, that is what we are actually trying to do it. So, now we can see that the first subsystem is actually like, so E1 tends to 0 when t tends to infinity, then for that you need to have E2 supposed to be 0. When this E2 supposed to be 0, where the tau properly you choose, so that it can be converged. So, for that we are actually like taking it this, the x2 dot, sorry, x2 decide, so which we have taken. So, then we are actually like bringing it. So, now you are actually like substituting this equation. So, from there we can actually like find that u can be one of the control input. So, this is what we can choose it. So, in order to actually like make it this more clear, so we will go with a Lyapunov you can say control stability proof. So, where we can actually like see that this is the x2 dot decide we can found, but here you can see that there is a small hiccup will come because x2 dot decide minus x2 are not same. There would be error, that error may actually like prolong somewhere. Okay. So, because so x2 decide is not obtainable by x2, because this is t tends to infinity only, this will be obtainable. So, in that sense there would be a residue. In order to make that residue go out, we can actually like modify this control law slightly different. So, for that we are taking a Lyapunov direct method, where we are taking a Lyapunov candidate function as in this form. So, where of E1 transpose E1 plus E2 transpose into E2. So, now this is actually like a positive definite. So, when this would be 0, when E1 equal to 0 and E2 equal to 0, then only the V would be 0, otherwise it would be positive throughout. So, that is what we are actually like taking it. So, now this is actually like a positive definite. So, this would be equal to 0 when E1 and E2 both are 0, right. So, then I can take the time derivative of above function along its state trajectory. So, or you can say Lyapunov function derivative along with its state trajectory. So, then it comes like this. So, we already know E1 dot and E2 dot. So, we can substitute that. Okay. So, this is actually like fulfill. So, for making a stability proof, so the V2 dot supposed to be negative definite. So, it should be 0 when E1 and E2 are 0, otherwise it should be negative. So, that is what we are trying to prove. So, for that what we are trying to take E1 dot already we know, and E2 dot also like we can get it. So, now you can see the E1 dot by substituting this error. So, you will get some residue term here, right. If it is independent, this is what going to come. Since so it is not independent, so there is a residue value. So, this value need to be compensated. Now, coming to E2, so E2 dot come like this. So, we substitute everything. Okay. So, then what we can see, if we choose u in this way, so what we can see, the U2 dot would be coming minus k2 E2 plus some residue term, right. So, this residue term and the other residue term what we obtain here, these two would be you can say cancel each other when we substitute into the Lyapunov function. So, when we substitute here, okay, when we substitute it here, so you can see like automatically these two terms will go out, and then you will end up with this. So, this equation ensure that it is negative definite. Okay. So, this would be 0 when E1 and E2 are 0, only if E1 and E2 are 0, right. Similar case to the V. So, in that sense the stability is proof. So, based on that if you take U, so this is what the final control input. So, now you can actually like convert into tau, because U equal to tau, and this become as actually like M, and this become as actually like a J, and this become as actually like K2, and this E2 become actually like Q dot decide minus Q dot. So, this Q dot decide we can write as, so mu dot decide plus, so K1 mu tilde multiply with J of Q inverse, like that you can actually like keep going. So, like that you can actually like make it. So, for example, I just wanted to show that. So, where you can actually like say, so what is x1, what is x2, these all we can actually like get it here. So, you can see. So, this is actually like x2 dot decide. So, you can actually like see this is, so x1 double dot means, so that would be mu double dot decide. So this becomes 0 because we have, so function of x1 is no value, and this is actually like mu desired dot, and this is actually like mu tilde, and this is actually like j, you can say dot of, so inverse. So like that you can actually keep substituting and use it. So in order to get this more clear, so we will do a MATLAB simulation in upcoming lecture. So with that we can actually close this particular content, then we will see some numerical problem. From there we can actually close this entire portion. So I hope you are actually clear on what is the cascaded control design, or what you call dual loop. So why it is called dual loop? Because it is having a, for example, I call this is a robotic system. The robotic system will give two things, so Q and Q dot. This Q dot would be compensated with the inner control, so where here Q desired dot would be calculated. Okay. So this would be actually calculated based on, you can say, forward kinematics, and you have actually a mu, and you will take mu desired and you will compare and you take a outer loop control. So that is why it is actually like a two stage. So the outer loop control will give the Q dot desired. So that is why it is called cascaded, but the dual loop, because the kinematic loop on the outer, so kinematic or outer loop, and dynamic or inner loop is inside. So this is actually like controlling tau, and this is controlling Q dot desired. Okay. So now if you use the old computing torque, or say computed torque control, the Q dot desired we can take it J, you can say Q desired inverse of mu desired dot. So we can see like the dynamic, which is actually like inner loop. So that is actually like making a small patch up where the robotic system, the outer loop is controlled in task space. That is the beneficial, so that you can actually do a proper motion control. However, the inner loop, which is controlling the what you call dynamics, that directly given in the task space, so the actuator can be controlled straightforward. So I hope so you are actually clear on this cascaded control design. So we will see the numerical example along with MATLAB simulation. There you will be getting more clarity. So with that, see you then. Thank you. Bye.